Today we're going to be continuing on our energy conversion, and we're going to dive a little deeper into the first law of energy conversion that I covered very briefly in the last lecture, and show some examples and try to get a little better understanding of what we're talking about and what the limitations do to us regarding the first law of energy conversion that says you cannot create nor destroy energy. And we're dealing with the middle box here where we're converting energy from one form that we find in its natural state to the form that society needs and wants and willing to pay for. And we've already been over this diagram looking at all the infrastructure that we have in order to carry out this conversion process. And repeating the first law, total energy cannot be created or destroyed is the first law. And that sometimes comes a little surprising because a lot of times in the press and the media and the public we talk about producing energy. But when we produce energy, we're always using energy on the other side somewhere. There's got to be an energy input before we can produce it from our hot air furnace or from whether automobile or for our wind turbine or something. There's got to be an energy source in order to produce energy. So we're never creating energy. We're only converting it again from one form to the other. So I can't say that enough. Now to dive a little deeper, we need to understand what types and forms of energy we're talking about here. What all are some of the different forms that we typically deal with? Well, work is one of the most valuable forms that we have, and that is, as an example, is a turning shaft that turns the axle to our car with a torque on it that drives our car, or when we pedal our bicycle, we're turning a shaft that powers the rear wheel that pushes us up a hill or against the wind resistance as we ride our bicycle. Electricity is another form of energy. And there, of course, that's a current and voltage that's carried over a wire. Electricity is a very nice form of energy because it's one that can be transported over long distances very efficiently. Work, you got to have a shaft to carry that work from one place to the other. So, of course, you don't want to have a mile-long shaft to carry work from one place to the other, but we can produce electricity in one place and carry it over a mile-long power line and then use it to power an electric motor on the other end, and that can produce our work. So electricity is one that is a very nice form of energy, but of course we don't find it in a natural state. We always have to generate it from some other source. Kinetic energy is one that we're probably fairly familiar with regarding a moving car. You have to put energy into the car when you're at a stoplight in order to accelerate it to 25 miles per hour to get to the next stoplight in traffic. So it has kinetic energy. And then unless you're dealing with a hybrid car, you put your brakes on, which produces friction and turns that kinetic energy into heat that heats up the brakes and dissipates that energy. That kinetic energy is dissipated into thermal energy and into the atmosphere. So it's wasted, so to speak. We put it into the car to create the kinetic energy, but then we don't get it back out. But a hybrid car uses a generator to link into the brakes, and the braking is done with a generator that generates electricity then and stores it in a battery to accelerate when we get ready to start back up from the stoplight. Thermal energy is, and that sometimes we call heat. It's one that a warm cup of coffee contains thermal energy. Any kind of object that has a temperature above ambient temperature, whatever the ambient atmospheric temperature is at that point in time, if you have any substance at a temperature higher than that, that's what we call thermal energy or heat. Hot air, hot coffee, a warm house inside, all of that's thermal energy. And this is another form of energy that we want a lot. And hot water to shower with is another place where we have thermal energy, or heat, sometimes we call it. Chemical energy is one that's in the chemical makeup with our electrons bonded to the other molecules into the nucleus of our atoms and molecules. And we can carry out a chemical reaction and release that chemical energy, or we can create more chemical energy by putting energy into it and driving the chemical reaction to increase the chemical energy. So gasoline is one that is an example there. Gasoline has chemical energy in it, and we carry out a chemical reaction of that gasoline with oxygen in the air, as we saw the formula when we were talking about oil, and that releases that chemical energy as thermal energy or heat, and produces a very high temperature flame that when we can use to heat homes or to heat hot water or drive a power plant. Radiation is the final example that I give you, and that's, of course, the best example is the sun's rays. The radiation coming from the sun is radiation energy. You also feel it in front of a fireplace. If you have a wood-burning fireplace, then and you have a lot of hot coals, those coals radiate that, and that's thermal radiation, we call it. But the sun rays, of course, and that radiation is one that we use in solar energy to produce electricity or produce hot water to heat our pools or things. So those are just some of the forms of energy, and we can convert these forms from one to the other, as is shown here. So we put energy into some kind of energy conversion system that was designed to take that form of energy, work, electricity, heat, chemical energy, kinetic energy, potential energy, etc., and convert it to some other form of work, electricity, that is one of the work, electricity, heat, chemical, kinetic, potential, etc. For instance, you can take work and put it into a generator, electric generator, and electricity comes out of the generator. So that's one of the energy conversion processes that we do a lot to produce electricity. We might put heat in by burning coal in a power plant and that boils steam and goes through a cycle and produces electricity also. Kinetic energy is, as I already mentioned, an automobile is one of the best examples of that. Potential energy, if the automobile is high on a mountain, then it has potential energy and gives up that potential energy as it comes down the mountain or comes down the hill. And you can easily convert kinetic energy from the dropping potential energy as you coast down the hill, whether it's a bicycle or a car. So we got potential energy coming in on the left-hand side, and kinetic energy as the vehicle or bicycle speeds up as you come down the hill. So all of these are energy conversion processes. Some of them are more complicated than the others. Some of them are more difficult to execute than others, but they're very important to use the energy forms that we find available to us on Earth to produce the forms of energy that we want in order to make life more comfortable. Taking an example, and I mentioned the bicycle coasting down a hill, that converts the potential energy to kinetic energy, and I just put some numbers on here to show. You don't need to know how to make the calculation. Some of you probably do. But just as an example, if you have a 10-foot high hill and you coast down a hill that's 10 foot high and you have no wind drag or wheel friction, bearing friction and rolling friction of the tire on the surface, then you could the bicycle would accelerate to 17 miles per hour. And that would be true for a car as well as for a bicycle. It's irrelevant of the mass. In the metric system, if it's a 3-meter high hill and you coast down it, you can ideally create 28 kilometer per hour speed. But that's the ideal. That's the upper limit. If somebody comes to me and says he can do better than that, then I am very skeptical about something because it's some way energy is being created from something else or created from nothing. So this is the upper limit if we have a frictionless process, ideal frictionless process with no wind drag and no rolling friction. But total energy is not created. Energy is merely converted from potential energy to kinetic energy in this. So this is a good practical example, one you can probably intuitively understand. But of course, we do the opposite when we climb back up the hill. We're adding potential energy to ourselves and to the bicycle so that we can coast down on the other side. Another example is we take natural gas chemical energy and we burn it with the oxygen in the air. A furnace is shown on the right-hand side. That's a typical warm air furnace, as we call it, in the U.S. The European and Western European and other countries don't have as many of the warm air furnaces. They have more water radiators. But this one burns natural gas and releases the chemical energy into a flame, and that warm thermal energy is then transferred to the air that's circulated from the house and fed, then blown with a fan back into the house. So warm air heat is added back to the air in the house from the chemical, the energy that started off as chemical energy in the natural gas. So the gas furnace is a nice energy conversion device, converting chemical energy to thermal energy or heat. So those are some examples, and trying to get a little better handle on what we mean when we talk about energy is conserved, total energy conserved, not kinetic energy is conserved or potential energy is conserved or chemical energy is conserved, but total energy of all of those added together of the earth or in our box that we're dealing with. You can't have more energy coming out than you have going in. Okay, thank you. Next time we'll deal with the second law in a little bit more detail. Thank you.